hope that's working. So the transport of gases and the control of breathing. So this is relevant or is in relation to how we breathe in oxygen and it is transferred across our alveolar membranes into our red blood cells, which then travel around the body, supplying our cells with necessary oxygen that they require. And without it, also the removal of CO2, without it resulting in the buildup of toxic chemicals, as well as the loss of oxygen required for the production of ATP, leading to necrosis and damage of our cells. And in rare cases, or actually not so rare cases, death. Cool. So to begin, we'll be talking about oxygen transportation. So oxygen is transported in two ways. It's either dissolved in plasma or bound to hemoglobin found in our red blood cells. The body consumes between 250 to 4 liters of oxygen per minute, with the latter being during exercise. The maximum capacity of blood for oxygen per liter is 200 mils at atmospheric pressures, where 197 mils of it is bound to hemoglobin and 3 mils is in plasma, showcasing that most of the oxygen in our body is bound to our red blood cells. When you're in the ward, you'll see that an oxygen saturation oxygen saturation is measured by an oximeter. This is usually combined with the pulse oximeter as well as the respiratory meter, as it calculates all of them at the same time and displays it on one screen. And basically what you need to be aware of is that if a patient has an oximeter reading of below 90, that patient is in hypoxia. If you look at our graph to the left, you might be wondering, if a patient's at 60, how can they be hypoxic if you look on the graph? As it says the resting physiological range of our red blood cell is between 40 and 100. Well, this is because the pulse oximeter is placed on your finger. And at this point, if the blood is at 60 or is at 90, excuse me, that means by the time it reaches your feet or any of the further extremities of your body, there's probably not enough there's definitely not enough oxygen to supply the tissue around it, and you'll begin having trauma in those areas. Next of all, then we'll be talking about the oxygen dissociation curve, or that curve that you saw just before. And this is known as a sigmoid curve due to the shape that it creates. And basically it indicates that as the partial pressure of oxygen falls, so does the percentage of oxygen bound to hemoglobin, which is exactly what we want as the red blood cells moves through the body, getting to areas of lower oxygen concentration. We want it to donate or release more oxygen to be provided to the tissue. If we look at it carefully, in the alveolar, the partial pressure of oxygen is 100 millimeters of mercury, and therefore there is 100% oxygen saturation of our red blood cells or hemoglobin, which is what we want. And as we move through the body, only 25% of the oxygen is removed. If we look at where 90%, only 25% of the oxygen is removed by the time it returns back to the alveolar. This allows for more oxygen to be provided if required, such as during exercise. The curve is relatively flat at its peak, meaning at high altitudes, oxygen saturation isn't affected too greatly, so we're still able to function. Next, we'll be talking about the factors affecting the oxygen dissociation curve. So a good way to remember this is that anything that your muscle does, so the more fatigue or the more work that your muscles do will cause the curve to shift to the right, allowing more oxygen to dissociate, therefore providing more oxygen for a muscle that is in work or under stress. And this is good because you want there to be more oxygen so it can work harder and perform whatever action you're trying to do with it. So a shift to the right means more oxygen readily dissociates from hemoglobin into the tissue. And the factors that affect it are known as the Bohr effect. And these are as follows: a decrease in pH, an increase in our CO2, an increase in temperature, and an increase in 2,3-diphosphoglycerate, which is a byproduct produced in the process of glycolysis, or glycolysis, if I'm correct, and that acts binding to an allosteric site found on our red blood cells, causing hemoglobin or more oxygen to dissociate from hemoglobin. A good way to remember it, in my opinion, is everything is increases except this part about pH. But if you think about it as increases in H plus ions, then you just have to remember everything's increase and just got to swap it around later. But it's up to you. And this is one of the things that they do test. If anything, you should remember these 4 factors or the Bohr effect for your exams. Next, we'll be talking about carbon dioxide transportation and diffusion. So carbon dioxide produced in our tissue then travels in our bloodstream in some manner, either A, diffused in plasma, B, bound to hemoglobin, or C, dissolved as bicarbonate, with it being the majority, which then is converted back into CO2 to be expelled during expiration. If we look at the image to the left, it's a nice summary of what actually happens in the red blood cells and how it occurs. So CO2 produced in cellular respiration, either A, combines with hemoglobin to form our hemoglobin carbon dioxide complex, or combines with water under the help of carbonic anhydrase to form our carbonic acid, which then dissociates into our hydrogen and our bicarbonate ions. The bicarbonate ions are then exchanged with chlorine ions or salts, or the ions that is dissolved from salt, or Na plus NaCl, and it is swapped out with chlorine ions to maintain the electronegativity within the red blood cells. This process is then reversed within once the blood cells, or once the blood reaches the alveoli, where it then forms CO2 and then is expelled. Although the partial pressure of CO2 is considerably lower than O2, if you didn't know that, due to its high solubility, it diffuses across the alveolar membrane in approximately a quarter of a second. So therefore, it's definitely fast enough to even to maintain CO2 expiration during exercise. Next, we'll talk about the control of ventilation, or the rate and rhythm that we breathe at. So normally we have a respiratory rate about 17 to 18 to 19 thereabouts, and basically this is controlled. We don't do it consciously, therefore something in our brain must control it unconsciously or automatically, and that is found by the neurons in the VRG, or our ventral respiratory group, and this is part of the pre-Botzinger complex found in our medulla. And this basically is modulated by chemical receptors, or receptors found from all across our body, some found in the lungs, some in the carotid arch, some in the periphery, as well as those found in the central area, or in the brain. And basically these receptors feed information up into the pre-Botzinger complex, or the VRG, to modulate the rate and rhythm that we breathe at. And here are some extra dot points if you like to read them. And the following slide is just more explanation of that. Next, we have the control of ventilation, or the chemical control, or our receptors that act to modulate or provide information to our VRG, or pre-Botzinger complex, to modulate the breathing. These are divided into our central receptors and our peripheral receptors. Peripheral receptors are pretty straightforward. They are located in our carotid bodies, as well as our aortic arches, and they directly sense our oxygen concentrations, our CO2, and our hydrogen concentration, or the pH. And these act to modulate or send information to the pre-Boltzinger area to be processed, and therefore then modulate and change the rate at which we breathe depending on the conditions found in the body. This is also true of the central receptors, which are located in the medulla, and however, these ones monitor CO2 indirectly via our H plus concentration or our pH. And because pH doesn't occur or change instantaneously, this process takes a while and it takes time to occur. And however, this process, although it takes a lot longer to occur, has a much greater effect on the rate of ventilation, being probably about 70% of the changes in ventilation is due to the effect of central receptors, whilst only about 30% is due to peripheral receptors. Over here to the right, we have a nice schematic that summarizes what happens. Now that we know that the effects of our central chemoreceptors is slower than that of periphery, why is that important to understand? Well, it's because the need to breathe, or our need to breathe, is dependent on our CO2 levels. And because that is detected slower than that of oxygen, our body can sometimes run into the issue where we don't realize we need to breathe before our O2 is too low. This is specifically the case in a dive, in divers who do free diving, where they hyperventilate before jumping down so they can spend more time underneath the water. However, because of this inhibition of the need to breathe, because their CO2 levels are already really low because of hyperventilation, they sometimes run into the unfortunate scenario that where their O2 levels drop below the point at which their brain blacks out, or where they black out, before they realize, or their brain realizes, that they need to breathe. And this unfortunately leads to them drowning.